Welcome back. In the previous video, we looked at simple threshold clustering method, and we saw that distance between data points was not sufficient to define the clusters. Density-based clustering solves this problem. This method is also referred to as dbScan. In density-based clustering, the number of neighbors for each point is considered 2. In order for a point to be eligible to join a cluster, it must have a certain density, which means it must have minimum number of neighbors. The algorithm is very similar to simple threshold clustering. It uses a threshold distance and a minimum number of supporting neighbors. Unlike threshold clustering, the method is free from any assumptions about how the data is distributed and copes well when the clusters are irregular shapes. Let's look at these 3 points. Unlike threshold clustering, density-based clustering can detect noisy points. If we look at the neighbors of these points, we can see that they have less than 3 neighbors, which is the density we are using for this example. In simple threshold clustering, these noisy points would have joined the 2 clusters together and ended up with one big cluster. The steps for this method are very similar to simple threshold clustering. The only difference is that for every point, we check if it is an eligible point to be joining a cluster. An eligible point means that it has a number of neighbors more than or equal to the density specified. If the point is not eligible, it gets marked as a noisy point and it's removed from the pool of points that are not clustered yet. Now let's look at how we use the dbScan module from the scikit-learn. dbScan can be imported from sklearn.cluster. The other libraries we're importing, we will later on see how we're using them. First thing we will do is we will generate our own data to cluster. We will use a function from the scikit-learn library, which is from sklearn.datasets.sampleGenerator, which is called makeBlobs. What makeBlobs does basically, it generates random clusters of data based on some parameters that we specify. The first parameter we will specify is the number of sample points. This is the total number of points that we will generate. These points are divided equally among the number of clusters. The centers is basically the center of each cluster. The points we will generate will be Gaussianly distributed. With Gaussian distribution, we need to specify the mean, which is the center, and the standard deviation as well. The standard deviation is basically how spread apart the points are from each other. And the last parameter is the seed for the random. In this case, I'm specifying the seed to be 0 because I want to make sure that every time I run this, I get the same results. But if you want to have random data every time, you can not specify the random seed and it will by default give you random data. So after I specified the centers, makeBlobs will know how many clusters we want to generate based on the number of clusters we're passing. It will return 2 things: the data that was generated and the labels of the data. Labels mean for each data point in which cluster it belongs to. If we look at X, which has the data, you will see it's an array of arrays. Every smaller array has 2 dimensions, which is the dimensions we specified inside the centers. There is 750 points, because that's the number we specified in number of samples. So if we want to plot this data to visualize it, first thing we need to do is separate the dimensions. We can use .t as X is a NumPy array, and .t is part of the NumPy library, which will return X and Y. It will return an array for the first dimension and an array for the second dimension. Then we can use plot from the matplot library and we can plot a scatter plot with x and y, and this is the result. So we can obviously see we have 3 clusters with the centers we specified: 1, 1, -1, -1, and 1, -1. And the total of points is 750 points. The first thing you always want to do before you fit a DBSCAN model on data is to standardize the data. We will use the standard scaler from scikit-learn library. What this function basically does, it transforms the data to a mean value of 0 and a standard deviation of 1. Now, on this data, you can barely see much difference because the data we generated already have the same standard deviation on both dimensions. However, this is very important in cases that are not like this. So let's look at a simple example here. In this example, I have 4 data points. The values for the first dimension have a range from 0 to 1. And the range of the second dimension is from 1 to 10. So if we look at these 2 points specifically, they both have the same value of the second dimension. And the first dimension, there is a big difference from 0.2 to 0.6 relative to the range of this dimension. However, if we want to calculate the distance between these 2 points, the distance will be significantly small relative to if we had the same difference in the second dimension. To see this, we can use the Euclidean distance from scikit-learn library, and we will print the Euclidean distances of the data to the data itself. So it will return a matrix of distances. Of course, the distance of the point to itself will be 0. And this will be a symmetrical matrix because we are calculating distance from the same data to the same data. But we can look at this value here, which is the interesting value you're looking at. The distance between these 2 points is just 0.4, but the distance between these 2 points, for example, is much higher. So if we use the standard scaler and we transform the data and standardize both dimensions, and we recalculate the distances, now the distances give us a better measurement and better comparison between 2 data points without any bias from any dimension. So the previous value we had 0.4, now we're having 2 point something. So just remember, before you perform DBSCAN, always standardize your data. Now let's go back to the data we generated. We will use the DBSCAN module from the scikit-learn library. DBSCAN takes 2 parameters. The first one is the threshold distance. In this case, we're specifying it to be 0.3. And the second one is the minimum sample points that will validate if a point can join a cluster or not. In this case, we're specifying it to be 10 because we can look from the data, we can see there's a lot of points near each other. So with a 0.3 epsilon, 10 seems like a reasonable value. After building the DBSCAN, we need to fit the model on a specific data. So by calling fit and passing the data, which is x, our data is stored in x, this model will be fit. It means it will run the algorithm and it will have the clusters. Now, if we want to find out how many clusters there are, from our DB model, we can call labels. Labels basically has the label of every data point in our clustered data, which is in this case mean in which cluster it belongs to. I'm using the unique function from the NumPy library, which removes any repetition of values. In this case, going through all the labels of the data points, it will keep only the distinct numbers, which is the label of the clusters. So if we had 100 points in cluster 1, only one of it will stay, and we'll only see one. By doing that, we can find out, just by counting how many labels left, the number of clusters. If we do so, we get a result of 4, which is weird because we know we had 3. The dbScan module gives a label of -1 to the outlier points, meaning the points that were noisy and were not clustered. So by using the same function unique from the NumPy library, we will pass another parameter which is return counts. And in this case, the function will return 2 values instead of 1. The array of the unique values and the counts of each one. If we print the values, we can see that there are 18 points with label -1, 243 with label 0, 244 with label 1, and 245 with label 2. So there are 18 noisy points. The count we got for clusters 4 was because -1 was counted with the other clusters. So basically what we need to do now, in order to get the number of clusters, is to do the same thing, but if we have a -1 as a label in the cluster, subtract the number of labels by 1, which we do here. We basically take the length of the unique labels and we subtract 1 if -1 is inside the unique labels. If -1 is not inside the unique labels, we subtract 0, which basically means we're not doing anything. Then we print the number of clusters, and in this case, it does return 3. Now we want to visualize the clusters. We've already visualized the points before, so we know how to plot the points in a scatter plot. But we want to add colors, a different color for every cluster. So we have the labels, and the labels are -1, 0, 1, and 2. So simply what we will do is that we will map a color to every label. For -1, we're going to specify the black color, for 0 red, for 1 blue, and for 2 green. We will go through the labels one by one, and we will assign the value color that is mapped to the label. So we created an array of the map here, and then we went through every label from the labels returned from the DB cluster model, and label underscore color will have an array of labels, but instead of -1, 0, 1, and 2, it will have K, R, B, and G. We separate the dimensions just like we did before, and then we use plot.scatter and we pass X and Y, and we also pass the colors. C is the parameter for colors, and we assign colors to the array we generated here, which has the color of every point. And we can see the plot. The clusters are clustered significantly well, and we can notice the outliers, and it actually makes sense. If we look at these points here, if we were using the simple threshold clustering, for example, that didn't check for minimum number of points, then most probably the whole 3 clusters would become one cluster.